So, welcome you all. This is a question which is based on underground cables, and this question has already been asked in ESC 2019 examination. So the question is like, a concentric cable has a conductor diameter of 1 centimeter and an insulation thickness of 1.5 centimeter. When the cable is subjected to a test pressure of 33 kilovolts, then what will be the maximum field strength? Right? So A, B, C, D are the four options. Out of these four options, only one option is correct, that we will have to choose the correct option after solving this numerical. So the question is clear. The question is, I repeat, a concentric cable has a conductor diameter of 1 centimeter and an insulation thickness of 1.5 centimeter. When the cable is subjected to a test pressure of 33 kilovolts, what will be the maximum field strength? So let me first derive the expression for the maximum field strength. So let us consider a cable. This is the underground cable, right? So we know that the underground cables are to be laid in areas where it is almost impractical to use overhead transmission line. For example, in case of transmission line through sea areas, or through crossover, or through terminal connections in substations, or through airfield crossings. So for all such areas where it is almost impractical to use overhead transmission line, we will have to use the underground cables, right? So this is the cable, underground cable, right? A small r is basically radius of the core or conductor, right? A small r is core radius or conductor radius. Capital R is the radius of the sheath. It basically includes the thickness with the conductor radius. That means small r plus t will be the value of capital R, that is the sheath, the radius. So you know the sheath. Sheath is basically used to protect the cable from the moisture, because moisture is harmful for the insulation, right? So aluminum sheath is cheaper and it can be used, right? Lead sheath, aluminum sheath. So sheath is basically, it protects the cable from the moisture, right? So it forms the outermost covering of the cable, that is basically sheath. So let us consider a section dx at a distance x. Let us consider a section dx, elemental section dx, right? Elemental section dx. Let us consider a elemental section ds at a distance x from the center of this cable, right? So the electric flux density at a distance x from the center will be dx, d suffix x. It will be expressed as charge q that is in coulomb per meter square. Electric flux density is expressed in coulomb per meter square. So that is Q by 2 pi x into the unit length of the cable, that is 1. So this is the expression of electric flux density at a distance x from the center of the core. So unit is coulomb. Unit is coulomb per meter square. Right. Now the dielectric stress at a distance x from the center of the core or conductor is given by E suffix s x, that is equal to d suffix x divided by epsilon, which is basically epsilon is basically the permittivity, which is equal to epsilon naught epsilon r. Epsilon is equal to epsilon naught epsilon r. Epsilon naught is the permittivity of the free space and epsilon r is the relative permittivity of the dielectric. So this is the expression Q divided by 2 pi x into epsilon, that is the dielectric stress. So we have now calculated the dielectric stress, right? So the unit is volt per meter, right? So let me give another notation to this for simplicity. Let me call this Gx. For simplicity, just for simplicity, I am noting down this dielectric stress Ex by another letter G suffix x. Gx is basically dielectric stress, right? So at a distance x is equal to small r, at a distance x is equal to small r, the dielectric stress G dielectric stress, it will be equal to Q divided by 2 pi epsilon, in place of x put small r. So this is the dielectric stress at a distance x is equal to r. At a distance x is equal to r, that means at the conductor surface, because you know that r, small r is basically conductor radius. So at a distance x is equal to small r, that means at a center at a distance x from the center, that is equal to radius of the conductor, the dielectric stress will be Q by 2 pi epsilon into r, right? Now similarly, if I want to find out the dielectric stress at a distance at x is equal to capital R, then I will have to write Q by 2 pi epsilon into capital R, right? So if I analyze these two expressions, Q by 2 pi epsilon into small r and Q by 2 pi epsilon into capital R, it is clear that capital R is greater than small r, because small r is the radius of the conductor and capital R is the total radius including thickness of insulation T. Small r plus T is equal to capital R. So capital R is greater than small r. So here definitely this at x is equal to small r, the dielectric stress, it will be the maximum. The dielectric stress will be maximum. Let me call G max, right? And at x is equal to capital R, the dielectric stress will be minimum, right? Because capital R is more than small r, right? So now if I want to calculate the potential difference between the conductor and the sheath, potential difference between the conductor, right? This is the conductor and the sheath. You know that the sheath is always at the ground potential, right? 0 volt. And this is the conductor. So the potential difference, if I want to calculate between conductor and the sheath, then the potential difference between conductor and the sheath, it will be equal to the work done to move a unit charge from the conductor to the sheath. To move a unit charge from the conductor to the sheath, right? So here I will have to write potential difference V is equal to small r to capital R and the dielectric stress Gs into dx. Just like you know that V is equal to integral E dot dl, right? E is electric field intensity. In the same way we have Gx, that is the dielectric stress, that is similar to Ex, right? So V is equal to integral E dot dl. In the same way we can write the same formula, V is equal to integral small r to capital R Gx into dx. So here just put the value of this Gx, that is q by 2 pi epsilon into x into dx, right? So here I can write q by 2 pi epsilon, and here I will write small r to capital R dx by x. So this is nothing but V is equal to q by 2 pi epsilon into ln this dx by x is ln x. Put the limit small r to capital R, you will get ln capital R by small r, right? So from here if I divide it by small r, then I will get, if I divide it by small r, then I will get V by small r is equal to q by 2 pi epsilon into 1 by r ln r by capital R. Or I can also write this expression in this way: V by small r ln capital R by small r is equal to is equal to Q by 2 pi epsilon into 1 by R, like this. So you just analyze this. Q by 2 pi epsilon R is nothing but the maximum dielectric stress or the maximum field strength, that is G max. Q by 2 pi epsilon into small r is G max, and that precisely we will have to calculate, right? That precisely we will have to calculate, right? So now our aim is just to put the values, right? So here you can simply put the values and get your G max. So G max is V by 2 V by small r ln capital R by small r, right? So from here you can calculate the dielectric stress, that is maximum dielectric stress. So V is, it is 33 kilovolts, right? And a small r is given as, see, the diameter is given 1 centimeter, so the radius of the conductor is definitely half, so that is 0.5. So 0.5 centimeter, you write 0.5, and ln of capital R by small r. So here you know that ln capital R is nothing but a small r plus thickness, right? Capital R is thickness plus conductor radius is small r. So thickness is 1.5, it is given 1.5, right? Thickness is given as 1.5 centimeter, and radius of the conductor is 0.5. So 1.5 plus 0.5 becomes equal to capital R. So becomes 1.5 plus 0.5 becomes 2. So 1.5 is the thickness, and here 0.5 is the conductor radius small r, that is capital R, divided by small r, that is 0.5, right? So 33 divided by 0.5 ln capital R by small r. Capital R is small r plus t is 1.5, small r is 0.5, small r is 0.5. So ln 1.5 plus 0.5 become 2, so ln 2 by 0.5, that is ln 4, right? So when you solve this, you will definitely get 47.6 kilovolts. So which option is correct? Option D is correct. Option D is correct. So that is the answer. Thank you very much. Thanks for watching.